Hello everyone, I'm Zhang from the Pacman Lab of Tsinghua University. Today, I'm very happy to introduce our MAGPY system here. This paper is entitled MAGPY, Compiling Eager Mode DNN Programs by Monitoring Execution States. It's common to write deep learning programs with Python and PyTorch because we can program very flexible with this ecosystem. However, as the program is too flexible, it is difficult to be compiled. So the programs are just run in PyTorch eager mode without compilation. On the other hand, as a system guy, we want to make the deep learning programs to run faster. So many of us have developed great deep learning compilers now. These compilers can significantly make the programs run faster. They usually require a deep learning operator graph as input, so that they can do some transformations on the graph to generate a faster one. And now the problem appears. The users prefer to write a Python program, but the compilers need the operator graph. Then how do we convert the Python code to the operator graph? This conversion is not trivial and will face many challenges. The first is the dynamic of Python. Python is a very dynamic language. It has dynamic data type, and the data type cannot be analyzed from the source code. Secondly, why we like Python? Because it is very easy to use. It has many flexible APIs to reduce our effort for developing new models. However, these great APIs are not friendly to compilers. The compilers need to understand these flexible APIs to generate the correct operator graph. Thirdly, the code may also contain some side effects, which is always a challenge to compiler design. Moreover, there is a large semantic gap between the programming language and the operator graph. The programming language is designed for users, so its goal is to make it easy to program so that the user will be very happy to use that. Therefore, the programming languages are becoming more and more flexible, such as Python. On the other hand, the operator graph representation is responsible for making the compilers easy to optimize them. So it should be as simple as possible so that the compiler can do better optimizations. For example, the users may write a deep learning model like the code in the left side. It will contain many lines of flexible Python code. But the compiler only wants the two operators in the program, I mean the reshape and the permute. It does not want to compile the Python logic. So the mapping between the user code and operator graph is not a one-to-one mapping. Thirdly, the operator graph may be changed during execution. An example is the Stable Diffusion model for image generation. During execution, it will call many different small models, I mean the LoRAs in this example. These LoRAs are for generating images with different styles. These LoRAs are changing during runtime, and we need to be aware of the change and provide the correct operator graph. It's common to compile the user code with just-in-time compilation. Let me introduce the procedure. Each compiled record will include an operator graph, which is needed by the graph-level deep learning compilers, and a guard function for verifying whether the upcoming request will run the exact operator graph in this record. And it also contains a mock that reproduces the side effect in the function. When the function is called, we first try to find a matched guard from the existing records. If we find a matched guard, we will run the corresponding operator graph and reproduce the side effect with the mock function. And if not, we will compile a new record, use the graph-level DNN compilers to optimize the operator graph, and add the record into the cache. The system we will discuss later are the different approaches for this recompile process. Two metrics are very important to the systems for exporting the operator graph. The first is safety. The system should generate proper guard so that it can pick up correct operator graph. The second is coverage. It needs to support a large number of Python features so that the users will be happy. As we will see, both metrics can affect the execution speed. Current approaches can be divided into two types. The first is trace-based. It records all tensor operations by overloading the functions for tensors. It allows the users to use almost all Python features. It's very good. However, it does not know what happens in Python, and thus it cannot generate the proper guards. To ensure the correctness, some of these works choose to re-execute the entire Python code in every run to generate the operator graph. This will result in large Python overhead. An example of this is gated tensor. It can lead to a 2.85 times overhead over an oracle created by us that runs a perfect guard and a perfect operator graph. Other work implement new compilers to analyze the operator graph, guard, and the mock. This time, it is safe and can generate proper guards because the compilers are designed for this. However, as the Python code is very flexible, these compilers can only cover a small subset of Python features. For example, the red box in the code cannot be supported by most analysis-based frameworks. They will cast the original program with the unsupported features and compile each piece separately. This disables many global optimizations and costs about 2 times overhead on average. And this experiment is tested on Torch Dynamo. Both approaches cannot balance the safety and coverage and lead to many performance issues. Can we achieve both coverage and safety at the same time, so that we can generate proper guards to ensure safety and to support a large number of Python features? We want to see that it is possible. Our system is called MAGPY. The core idea of MAGPY is using the execution state information from the Python interpreter to help our compiler make better understanding of the user code. Why do we choose to use the information of Python interpreter? First, Python interpreter is a neutral software that accurately supports all Python features. It is indeed the software that provides the best coverage of Python. Secondly, Python interpreter maintains many high-level information of the execution states. For example, we can directly get the type and value of a variable from the interpreter. There should be some valuable information for our analysis. Our design is based on the following observations. First, deep learning programs are executed in batch, and the operator graph structure between different batches are seldom changed. Though the graph indeed will change, but it will happen very seldom. Therefore, we can use an approach similar to the tracing approach to get the operator graph. But different from trace-based approaches, we need to further know whether the graph will change during either following execution. So when will the graph change? We find that only the external variables can influence the structure of the operator graph. What is external variables? They are the ones highlighted in the colors in the example code. They are the ones that exist at the outside of the function, like the input variables, for example, the x, dims, and self in this example. And there may also contain some global variables. As long as these variables do not change, the program's execution result will remain the same. For example, in this code, as long as the x.shape, dim, self.scale, and self.dim is unchanged, the operator graph will be the previous one. So many complex Python operations are used in this function. They will not change the operator graph. So we only need guards on these external values that are marked in color. We now know the set of variables we need to generate guard. Then how to generate the guard for them? We find that we only need the value of these variables. And we call the value of these variables the execution states. For example, the guards is for validating whether the values of the external variables are the same with the previous run. And also, the mock generation is also only use the state information. The only difference is it needs the value of the final state. For example, if we find a program that writing a value 3 to a global variable x, we then do not care whether the value 3 comes from 1 plus 2 or from 6 divided by 2. As long as we know that the x is updated to 3, we can generate a mock that updates the global variable x to 3. This is very different from the analyze-based approaches that analyze the full logic of the program. Execution state information are enough. This is a very important property because the execution state can be easily collected from the Python interpreter. For example, we are able to get the value of a variable by querying it to the interpreter with the variable name. And the last question is that which problem states are needed by us? From previous analysis, we know that we need to check the external values, like self, that usually represents the model structure. And in addition to that, we also need to check the values referenced by these external values. For example, self.n layers that usually represents the number of layers of a model. To manage such reference relationship, we introduce a reference graph to save the program state. Here is an overview of our system. When we fail to find an appropriate operator graph from the existing records, we will use MAGPY to recompile the user program. The smallest granularity of Python program is Python bytecode. And after the execution of each Python bytecode, MAGPY will examine the execution state of the Python interpreter so that it can update the reference graph. And when the user program ends, we will analyze the reference graph to generate a new record. And here is the whole overview. First, I'll introduce the reference graph. It saves the execution state during execution. Each node in the reference graph represents a Python object. For example, this example user program creates a tensor and then calls a function with a list containing that tensor and a value 2. So that this reference graph contains 3 nodes, the SN1 for the list of tensor, and the SN2 for the tensor in the list, and SN3 for the value 2. And we also create a special node SN0 to represent the external execution state of the function. And the edges between the nodes represent the reference relationship between the objects. For example, the x variable of the function are bounded to the list. So there is an edge from the SN0's external to the SN1's list, and the edge attribute is x. And similarly, there is an edge between the external SN0 to SN3 and marked with y. And there is also a relationship from SN1 to SN2, the tensor, because the list contains the tensor. And we also introduced the version concept. The goal of the version is to track the in-place update of the variables. For example, the in-place update of the tensor in this line of code will add a new version to SN2 for the tensor. And this line contains 2 operations. It first computes a new tensor x0 multiplies y, so that we add a new SN4 node to the operator graph. Then we append the new tensor to the list x. It is an in-place update to the list x, so that we add a version to SN1. And this line will create a new node and add a version to the external. In addition to the reference graph, we also record as an operator graph. It is very similar to the normal operator graph. And in addition to the normal graph, we also record the node ID and the version ID in the reference graph for each tensor node, so that we can know which Python object the input tensors are goes from, and which Python object the output tensors are written to. Some functions in Python are implemented with the low-level C language, so Python interpreter do not know its behavior, and thus MAGPY cannot collect the behavior information of these functions from the interpreter. we introduced some annotations to provide the essential information for the MAGPY system. For example, annotations for in-place update. Note that these annotations are already written by us in the MAGPY system, and the users of MAGPY do not need to write these annotations unless they have written some new C functions. When the program ends, we generate a record based on the reference graph. The guard is for validating whether the initial state matches the previous run. So we need to find all reads to the initial state before the program execution. All variables that need to be guarded can be collected by traversing the reference graph from the external node SN0 and only via the edges on the first version. For example, in this code, we need guard on SN1, the list X, SN2, the input tensor, and SN3, the float value 2. And the mock is for reproducing outside effects. So we need to find all effects to the final state after the execution. It contains two parts. First are the values directly written to the final state, like the variable A. So we can find such variables by traversing the graph with the last version as H. And also the in-place update to the input variables, like the in-place update of X. This node exists as the initial state and will contain multiple versions, like the SN1 for variable X. Our system can also handle some dynamic scenarios, like dynamic scalar, dynamic shape, and dynamic control flow. You can check our papers for details. Our MAGPY system can be enabled by adding only one line of MAGPY.compile to your deep learning model. This line can bring about 3 times speed up over the eager execution. We evaluate MAGPY on A100 GPU. First, we want to know how many pattern features our MAGPY can support. We use Parity Bench. This is a benchmark that collects more than 1,000 real deep learning models from GitHub. They are all real models, and we try to compile them without modifications to the user code. TorchScript can convert 35% of models to a complete operator graph. TorchDynamo can convert 77% of them, and MAGPY can convert 93% of them. The second part is end-to-end evaluation. We want to compare exporting operator graphs with different approaches, and then use the same graph-level compiler to compile the graph. We can achieve 1.8 times speed up over TorchDynamo, 1.78 times speed up over TorchScript, and 2.49 times speed up over lazy tensor. When we need to compile a new record, the monitor overhead of MAGPY is tolerable compared with the time needed to compile the new operator graph. And when we can reuse a record, no new overhead will be added by MAGPY. In conclusion, our MAGPY system is for compiling eager mode deep learning programs written in Python and PyTorch. It uses the execution state information from the Python interpreter to improve the quality of generating operator graph. It can export 93% of over 1,000 models to its complete operator graph and achieve up to 2.88 times speed up. That's all. Thanks for your listening.